about a couple of orders of magnitude, from either of these two platforms. Now, associated with these length scales are energy scales. So in quantum materials, typical energy scales are of the order of 100 or 1,000 Kelvin. In cold atoms, we're at 0.11 nanokelvin. Moiré Quantum Matter, because we're at intermediate length scales, we're also the intermediate energy scales, the 1 at 10 Kelvin, 1 at 100 Kelvin. Now, the thing that has made this possible, this Moiré quantum platform, is something which for which there was no precedent in the history of material science, which is the ability to vary the twist angle between two crystalline lattices completely at will. Okay, so with the advent of 2D materials, we were able to not only place them on top of each other, that already gave us a lot of freedom, but we were also able to put two 2D crystalline lattices at any angle that we choose on top of each other. Okay, and that is a knob that twisting, which sometimes people refer to twistronics. That's a knob that was not present there, earlier. Okay, and as I'm going to show you, by twisting two 2D materials, you can actually vary a lot the electronic, optical, mechanical properties of the system. I will focus on the electronic properties in a very dramatic way. So with this, let me tell you, so this is the outline, this is what I want to tell you about. I'll remind you of what graphene and magic angle graphene is, and in particular, what have been the developments since we announced our discovery a few years ago in the field of Moiré Quantum Matter. And then I will introduce you the next generation, Moiré Quantum Matter system, which I call Moiré Magic 3.0. It's Magic Angle Twisted Trilayer Graphene. It's a much more highly tunable system than the bilayer case. It realizes ultra-strong coupling superconductivity, and I will show at the end an unexpected surprise related to in-plane magnetic field measurements. This system is likely a spin triplet superconductor. And then I will tell you just a little bit about some of the outlooks, what else is going on in nearby fields. So let me remind you, everyone, what graphene is. Graphene is a honeycomb of carbon atoms. Okay? All of these atoms are carbon, so they're chemically equivalent. However, from the crystallographic point of view, you need a 2-atom basis in addition to 2 unit vectors to tile a honeycomb in 2 dimensions. Okay, so we call these the A and B sublattices, or the red and green balls here in this drawing. Now you can calculate the electronic structure of graphene. It's a very famous electronic structure: energy versus momentum in the x and y direction. Near the Fermi energy, you have these linear energy momentum dispersion, which is more reminiscent of the way photons travel rather than electrons in typical solids. Okay, now this electronic structure can be formalized into this Hamiltonian equation. Okay, I think this is about the only, maybe one more formula in the entire talk, so don't worry. Here you have energy is linear in momentum. This is Pauli matrices, and this, which in the this equation is nothing else but the Dirac equation in 2 dimensions for massless particles. In the Dirac equation, you have this spinor, which tells you whether the electron spin is up or down. In the case of graphene, this is a pseudo spinor, which tells you whether the weight of the electron wave function is on the A or on the B type sublattice. Okay. Now, the only other thing that I want you to know about graphene is that we have 2 of these double Dirac cones. We call them valleys, and they're called the K and K prime valleys. So we say that electrons in graphene have this 4-fold degeneracy, or these 4 degrees of freedom. You have your electrons with spin up, spin down, valley K prime. Okay, just remember number 4. Now, what happens if you put graphene on top of graphene and you twist the lattice? Okay, a Moiré pattern forms where the Moiré wavelength, okay, the distance between the soccer balls that you see here in the animation, is roughly proportional to 1 over the twist angle. Okay, now this is what happens in real space. Let's think about what happens in momentum space, and in particular, what happens with the electronic structure with those Dirac cones. Okay? Now, I'm showing here what happens when you have, the Dirac cone, from one layer of graphene and the Dirac cone from another layer of graphene, okay? Because we have rotated by a small angle, those 2 Dirac cones in reciprocal space, they separate also by a small distance in momentum space, which is proportional to the angle for small angles, okay? Now, this was studied by many people. And now, if, this is the electronic structure that would be realized if the electrons did not know in one layer did not know that the other graphene layer exists. However, because these two graphene sheets that we place on top of each other are only 3 angstroms apart, electrons can very much tunnel between the layers, okay? So that interlayer tunneling leads to bonding and anti-bonding states at this point, at this crossing point, okay? So that you get one band which gets pushed down, the bonding band gets pushed down a little bit in energy, anti-bonding band gets pushed up in energy, okay? This is exactly the same as hydrogen molecules, bonding anti-bonding states in a hydrogen molecule, but now with 2 giant graphene sheets. So it's a giant graphene molecule if you want, yeah? Now, the situation here is realized when this interlayer tunneling is much smaller than the energy of that crossing point. However, as you decrease the twist angle, these 2 Dirac points get closer and closer, so this bonding band gets pushed down to lower and lower energy until it gets pushed down to 0 energy, okay? When this is realized, we say that a flat band condition has been reached, and this occurs at the magic angle. That magic angle value for graphene on top of graphene is 1.1 degrees, okay? There was, work about a decade ago, both theoretical, predicting this angle, and experimental in the group of Ivan Drey, where they could explore the single particle physics associated with this magic angle, okay? In particular, they saw they could measure in STM a function of singularity that occurs at this energy and that goes to 0 energy as you reach these values, these angles, okay? So there was interesting, single particle work, both theoretical and experimental, about a decade, ago already. Now, that thing that I showed you before was a cartoon. This is an actual calculation of the electronic structure, energy versus momentum, okay, for magic angle twisted bilayer graphene. You can see this is a set of flat bands, okay? They're not 100% flat. There is a little bit of dispersion, but these are much, much flatter than the original graphene dispersion, okay? These blue bands are the remote Moiré mini bands, okay? Now, flat band in momentum space, okay, what happens when you put, when we place electrons in those flat bands? Where do they like to go in real space? So remember, to go between momentum space and real space, you have to do a Fourier transform, okay? So a Fourier transform of a flat object is a highly peaked object, okay? So if you look at where do the electrons like to go when you place them in these flat bands, they like to go in regions where locally the registry between the 2 graphene sheets is such that all of the carbon atoms in layer 1 are underneath the carbon atoms in layer 2, okay? We call those regions AA stacking, and there is where the electrons like to sit, okay? These regions are tunnel-coupled by regions of AB and BA stacking, where due to the small twist angle, the registry of the atoms comes, sort of out of sync, okay, and creates these AB-BA stacking regions. So from, schematically from the top, this is the way magic angle graphene looks like. We have regions of AA stacking, where the electrons like to be, and those regions are tunnel coupled by regions of AB and BA stacking. In a slightly more realistic, schematic, we have these AA regions, which here have these yellow circles, where the electrons like to be. These regions are 13 nanometers apart, okay? And this is going to be the equivalent of our triangular Fermi-Hubbard lattice, okay? In analogy with cold atoms, except that this system has very interesting topological properties, and you cannot truly map directly to a standard Hubbard lattice, okay? These ABBA regions form a honeycomb plaquette. They're not identical, okay? I will just mention a little bit more about this later. Now, so what we discovered in, back in 2018 is that if you put your Fermi level in those flat bands, you get at certain, numbers of electrons per Moiré unit cell or numbers of holes per Moiré unit cell, you get correlated insulated states. Yeah, your system is an insulator, even though your Fermi energy is in the middle of a band. Okay, and it should be good metal. That occurs only for a relatively small range of angles around that 1.1, roughly between 1 and 1.2, maybe a little bit larger. And to the surprise of, this was already a big surprise, but an even bigger surprise was the fact that, if you dope away a little bit from these correlated insulator states, your system becomes a superconductor. Magic angle twisted bilayer graphene becomes a superconductor, okay? And not just any superconductor, okay? It is an electrically tunable superconductor, okay? So, in Magic Angle Graphene, we can measure the resistivity versus temperature and charge density. We can vary continuously the charge density electrostatically, because our Magic Angle Graphene is one plate of a parallel plate capacitor with another metallic plate. We can apply a voltage to vary the charge density in our plates. Okay, so we can vary the charge density continuously, and at a filling of 2 holes per Moiré unit cell, we found a correlated insulator state. If we add extra holes, we find superconducting dome. If we add electrons, we have a superconducting dome. Okay. Now, when my students show me this, it immediately reminded me of the hundreds of times I've seen this type of phase diagrams. Okay, these are the phase diagram of the couplet family of high temperature superconductors. In a temperature versus doping diagram, let me flip this axis for electron hole doping so that they look the same as here. Okay. Now, at 0 doping, which means 1 electron per unit cell for the couplets, it's a mod insulator. You add extra holes, you have a big superconducting dome. You add electrons, you have a smaller superconducting dome. Okay. Now, of course, the difference between this and this is that this is a phase. An important difference between these two is that this is a theoretical phase diagram. Okay. In order to populate this diagram with actual experimental data points, you have to grow hundreds and hundreds of crystals with different chemical composition, different disorder, and often from different material classes, because not every material can be grown, with the same, in different dopings. Okay. In this case here, this is all done in a single cool down with a single desolderization without the introduction of chemical impurities, and we can go from here to here in a few seconds. Okay. So that is one of the things that attracted a lot of attention. There are many similarities, also many differences between these two systems. Now, so we posted, we announced this in the APS March meeting in 2018. Okay, the actual paper was published in April, and then after that, the theory tsunami came. Okay, this is just a small, list of the papers that appear within a few weeks of us posting our paper. By now, there are several thousand of these papers. A lot of people are interested in determining what is the origin of the correlated insulator state and what is the superconducting order parameter. Okay. Now, all kinds of theoretical proposals have been put forward. Started with Senke, Xu, and Leon Balent's proposal for D plus ID chiral topological superconductor, and then everything, S, P, D, S plus C plus D, F, D plus ID, you name it, all kinds of order parameters with all letters of the alphabet have been proposed. I'm not going to discuss much about this, because I think the situation still remains very much to be fully understood. Now, this thing attracted also a lot of interest from the popular press, with people, articles, in various journals and Quanta and so on, with very cool pictures. Let me tell you a little bit about what has happened since our discovery. Okay, so again, the paper was published officially in April 2018. So what has happened since then? The first thing that happened is that we have reproduced our own results. That's good. When it happens, it doesn't always happen. So it's good when it happens that you can reproduce yourself. Okay. Since then, we have made many, many, many more devices. Okay. This is actually a bit old, actually. In fact, by now we have even many more data points. We're starting to determine the community what's the critical temperature at optimal doping as a function of twist angle. So a superconducting dome, but in this new parameter, twist angle, which wasn't present there before in material science. Okay. Now, even better than you reproducing your own results is when other people completely independently of you reproduce your results, okay, and even extend them to other systems. So this has happened, since our discovery plenty of times. The first, 2 papers to reproduce our results was, the first one was a collaboration between the group of Corey Dean at Columbia University and Andrea Young at UC Santa Barbara, where they were able to not only reproduce our results, but tune the superconductivity with pressure, okay, and confirm that indeed is associated with the presence of those flat bands. And then a group of, the second group to reproduce our results was the group of Dimitri Efetov, where they saw that in one device, they could measure additional superconducting domes, okay. Now, by now, robust superconductivity in Magic Angle twisted bilayer graphene has been reproduced and extended by many, many groups, okay, about a dozen groups, and more and more are joining. Now, we have discovered since then several other correlated systems, based on this Moiré physics and in twisted physics. For example, magic angle twisted bilayer graphene. This is a system where now you have regular bilayer graphene, okay? 2 layers of graphene with 0-degree angle between them. Another bilayer graphene, and now you twist them pairwise, okay? 2 twisted with 2. So you form this magic angle twisted bilayer graphene. It's an interesting correlated system with interesting magnetic properties. It is not superconducting though. Now, the other thing that has happened is that we start to have various scanning probe microscopy studies of the system, so we can look more microscopically what is indeed going on with these Moiré systems. Okay, and this has produced very interesting data. The phase diagram that we had until this scanning probe microscopy studies arrived was entirely from global transport measurements, such as the one that we do in my group. Okay, and just to remind you, so in a temperature versus a filling factor, this is charge density, okay, or the open if you want diagram, okay. Now, in these flat bands, okay, due to this spin up, spin down, valley K prime, degrees of freedom that I told you from electrons in graphene, we can put, from bottom, starting from charge neutrality, from 0 energy, we can put up to 4 electrons per Moiré unit cell, or we can empty 4 electrons or put 4 holes per Moiré unit cell. So we can put a total of 8 electrons per Moiré unit cell in the system, okay? We typically call that filling factor nu, which tells you the number of electrons or holes per Moiré unit cell that you have in your system. Okay? 0 is charge neutrality. And what we saw in transport through several studies, okay, this is just schematic, okay? Details can vary depending on the twist angle, etc. But roughly what we see is that features appear at each integer, okay, of a number of electrons or holes per Moiré unit cell, okay? Particular at 4 electrons or 4 holes per Moiré unit cell, you either have completely emptied this band or completely occupied this band, so you have single particle band insulators. But then, as I mentioned, at other integer filling factors, you have correlated insulator states, which cannot be explained by single particle physics, okay? Because your chemical potential is there in the middle of a band. Okay? Now, you also have some correlated semi-metal states at other integers. The situation is, can be complex. Let me not focus too much on that. When you dope electrons or holes around those correlated insulator states, you have superconducting domes. The most robust is this one. Okay, the second most robust is this one, and these others are seen depending on the device quality, the type of device, the twist angle, etc. So this is what our understanding was of the system based on global electronic transport measurements. And then 2 interesting studies, one by my group in collaboration with the group of Shah Halilani at the Weizmann Institute, and another one by the group of Ali Yazdani. We both use scanning probe microscopy techniques. Yazdani used STM, and our group used a scanning single electron transistor to measure the thermodynamic properties of the system. Okay. Now, in particular, we measured the inverse compressibility, which is the derivative of the chemical potential with density. So how does the chemical potential vary in your system as you add charge to your system? Okay. For this, we use a scanning single electron transistor, which is a very sensitive voltmeter. It can measure the voltages very sensitively. And in particular, it can measure this d mu dn, this inverse compressibility that you can think of in single particle physics as the inverse density of states. So for example, gaps appear as high peaks because in a gap you don't have density of states, so you have a peak in the inverse compressibility, okay? Now what we saw, what we saw is that if you look at a sample and you look at regions with different twist angles, around the magic angle, 1.1 degrees and nearby, what we saw is that there are these sawtooth behavior in the inverse compressibility where some feature appears at each integer, okay? Let me zoom in into one of these here. Okay, so you see this sawtooth behavior appears near each integer, okay? In a simple picture to 0th order, we understand now that the following is taking place. As you start from charge neutrality, your system has these 4 flavors, okay, that it has to add charge to. Spin up, spin down, valley K prime, okay? Now, as you add charge to your system, as you increase your filling factor, these 4 flavors start to get filled all at the same time, at the same rate, Now, when you are near filling factor, total filling factor 1, meaning each of these flavors is near 1/4 full, the system, due to strong Coulomb interactions, decides to spontaneously flavor, send all of the charge carriers into one flavor. These colors are giving you the occupancy of each flavor. So one, all of the charge carriers go to one flavor, and the other 3 flavors get emptied. Okay, and then you start again. You fill these 3 flavors when you're close to nu equals 2. So the 3 remaining flavors close to 1/3 full each. The system again spontaneously flavor polarizes, sends the carriers to another flavor, and empties the other 2, and you start all over again. This is called a cascade of phase transitions, okay? And in a simple model of Coulomb interactions, you can capture this inverse compressibility sawtooths happening near each integer, okay, which resembles what is seen experimentally, okay? And more complicated models have been developed since. Yeah? So we have this cascade of phase transitions at each integer, okay? That will appear later in my talk. Now, the other interesting thing that has happened since, many more things have happened, but those that I'm highlighting is that, the observation of ferromagnetism, anomalous Hall effect, and even quantum anomalous Hall physics, which brought front and center topology into this field of correlated Moiré systems, okay? So, in fact, for me, one of the most interesting things about this field of Moiré quantum matter is that it has meant the merging of several modern condensed matter communities that did not always interact so closely. So one is the 2D van der Waals materials and heterostructure communities, the people that worked on graphene, such as myself. Another one is the people that work on more traditional strongly correlated materials, cuprates, pnictides, etc. And then the people that worked on topological condensed matter physics, quantum Hall physics, topological insulators, etc. All 3 come together in this field of Moiré quantum matter, and I'm enjoying a lot my interactions now with people from these other communities. So let me tell you about this, next generation Moiré quantum matter, okay? So as of last month, okay, my group and also the group of Philip Kim, we published, the same week, we published in Nature, they published in Science, the discovery of a new robust Moiré superconductor, Magic Angle twisted Trilayer graphene, okay? So let me show you about this system. So this is the structure, okay? Now it is 3 layers of graphene where the bottom and the top layers are exactly aligned, 0 degrees with respect to each other, and all of the carbon atoms in layer 3 on top of all of the carbon atoms in layer 1, okay? The middle layer is rotated by an angle, theta, okay? So from the top to the bottom, you add the second layer rotated at an angle minus theta, and then you add the third layer rotate back by theta so that it's exactly aligned with the bottom layer. This structure has mirror symmetry with respect to the middle layer, okay? This structure was proposed by Eslam Khalat, the group of Ashwin Viswanath at Harvard, okay? And it's called A twisted A stacking because the first and the third layer, the bottom and the top layers are exactly on top of each other. Now, related work on mirror-symmetric MA-TBLG, has been published by several people, and also on other twisted tri-layer and multi-layer systems. Okay? Basically, by now, the theoretical community is calculating all of the structures that you can make with any number of layers of graphene, and calculated their electronic structure. Now, this structure is quite interesting because essentially you have these 3 layers which are coupled with a tunneling, element T between each layer. Okay, the tunneling strength between consecutive layers is T, and it turns out you have a 3x3 Hamiltonian where you can do a basis transformation such that the system becomes Hamiltonian becomes block diagonal. One block is a magic angle twisted by layer graphene like block, but with a tunneling element square root of 2 times T. And the other block is a 1x1 just monolayer graphene block. Okay. Now, this means because of this square root of 2, remember, I told you earlier that the interlayer tunneling determines what's the magic angle. Okay. So because we have here a square root of 2, the magic angle for magic angle twisted trilayer graphene is the one for the bilayer times square root of 2. So it's 1.1 times square root of 2, 1.56 degrees. Okay. Now this structure, okay, and sorry, and this means, by the way, that the Moiré wavelength, which I told you for magic angle bilayer was 13 nanometers, because now the twist angle is a bit larger, the Moiré wavelength is smaller. It's about 9 nanometers for the system. Okay. Now the system, again, this trilayer electronic structure is, bilayer graphene-like electronic structure plus monolayer graphene. Here you have it. Okay. When you do not apply a perpendicular electric field, so under mirror symmetric conditions, then your energy versus momentum has this orange flat band, which is, a magic angle twisted bilayer graphene-like flat band, and then it has this massless Dirac dispersion characteristic of graphene, and these two are orthogonal, these states at zero displacement field. Okay? Now, in our system, we have our magic angle twisted trilayer graphene, and we have top and bottom metallic electrodes. This allows us to independently vary the charge density in a twisted trilayer graphene, and also polarize your layers by applying a transverse displacement field by putting opposite voltages to the bottom and top layers. Okay, so when you apply a transverse displacement field, then you break the mirror symmetry of the system. Okay, the top and the bottom layers are no longer symmetric, and as a result, your electronic structure now gets hybridized. Okay, those two block diagonal terms now get hybridized, and your massless Dirac band and your magic angle bilayer graphene-like flat bands, they get hybridized, and this is tunable with displacement field. So the system is a lot more tunable. Okay, all right. Let me show you first that the system is a robust superconductor. Okay, so first thing that you want to see is zero resistance. Okay, so indeed, if you measure the resistivity as a function of temperature, you have this big drop to zero. Okay, you can fit this with the Halperin-Enso formula, and it gives you the BKT-Berezovsky-Kosterlitz transition temperature, which is 2.3 Kelvin for the system, and the TC 50% normal state resistance about 2.9 Kelvin. Okay? Now, the next thing you want to do is you see that this is truly a superconducting state, that it has flat, you can run a finite current bias and there is zero voltage dissipation. Okay, so flat VI characteristics with a sharp switching. And indeed, you can see this is present. Okay, you can do temperature dependence. You can analyze this to extract your BKT transition, which coincides with what we extracted from the temperature dependence. Okay, now, the system is also an electrically tunable superconductor, similar to the bilayer case. Okay, so we can measure the resistivity as a function of temperature and filling factor. Okay, similarly, the charge density here is normalized, by multiply by 4 and divide by the superlattice, density. So this filling factor tells you how many electrons or holes you have per Moiré unit cell. So we have here a large, around 2 holes per Moiré unit cell. We have a large superconducting dome if we add extra holes. We have a smaller superconducting dome if we add electrons. Okay? If we look around 2 electrons per Moiré unit cell, we have similarly a larger superconducting domes for the extra electrons, and a smaller dome when we dope with holes with respect to this electronic system. Okay. Then the last thing we want to do to check there is robust superconductivity is check what happens in a magnetic field. So if you are near optimal doping, where the superconductivity is very strong and uniform in your entire sample, you apply a perpendicular magnetic field, you kill initially superconductivity on a fast scale of order 100 millitesla, with then a long tail up to about half a Tesla. Okay. If you now change your density close to the edge of the superconducting dome, where the system is starting to break into superconducting islands separated by non-superconducting islands due to disorder, for example, okay, then if you measure your critical current as a function of perpendicular magnetic field, you can observe these Fraunhofer-like oscillations, okay, which tells you that there is Josephson phase coherence because of these superconducting islands, which are coupled by non-superconducting regions, okay? So all of these 3 features that I told you show that this is a robust superconductor. In fact, it is the second Moiré superconductor, beyond, the first Moiré superconductor beyond the bilayer case, okay? Now, let me show you that this is a very highly tunable system. Okay, so as I told you, we have these two knobs: the charge density or filling factor and the electric displacement field. Okay, so this is what happens when you measure the resistivity as a function of filling factor. Okay, again, from -4 to +4, so from 4 holes per more unit cell to 4 electrons per more unit cell, and as a function also of the displacement electric field applied in the perpendicular direction. Okay, now this is a pretty complex phase diagram. Let me guide you through it. These light blue regions are regions of superconductivity. Okay, you can see superconductivity appears mostly between filling factors 2 and 3, and -2 and -3, but you have also these other superconducting branches. Okay. Now, highly resistive features are in yellow. Okay, so for example, at the charge neutrality point, and then close to some other integers. Okay. Let me concentrate. Now, depending how you look at this diagram, you can focus on the symmetries or on the asymmetries. Yeah. Let me focus first. As you can see, there is top-down symmetry. Okay, this means the system is quite symmetric with respect to displacement field. Okay, you can see these features. They're also here. These features are also here. These features are here and here. They're quite symmetric with respect to displacement field, top and down. Now, left and right. Now the situation is a bit more complex. You can focus on the symmetries. For example, indeed, superconductivity is mostly between 2 and 3 and -2, -3. Or you can focus on the asymmetries. Okay, for example, these bright yellow features are not as present and as pronounced here. Okay, so this is actually something quite similar to magic angle twisted bilayer graphene. With respect to charge neutrality, you have a certain degree of asymmetry in the system. Okay, now because this is so complex, we can try to measure other quantities and see if they correlate with what we observed in this phase diagram. And what we decided to measure is the normalized Hall density. So this is the Hall density, okay, which is proportional to 1 over the Hall voltage. Okay, now multiplied by 4 and divided by the superlattice density. Okay, so that we can normalize this and call it the normalized Hall density, analogous to the filling factor that I told you earlier. Okay, this is now the normalized number of free carriers per unit cell in your system, so to speak. Okay, now if we measure this normalized Hall density, okay, as a function of again filling factor and transverse displacement field, you can see again that it's a complex phase diagram. Okay, now to 0th order, most of the features that we see in this diagram can be associated with one of the following 3 situations. Okay, the first is a behavior which is characteristic of a Dirac point or a gap. Okay, where your normalized Hall density changes sign, crossing smoothly through 0. Okay, remember at a gap or Dirac point, okay, your carrier density changes sign smoothly and goes through 0. So your normalized Hall density does the same thing, goes smoothly through 0. This happens, for example, here at charge neutrality, where the system, the Fermi energy goes through a Dirac point. Okay, you can see here that you go from dark blue to light blue to white, light red, and then darker red. Exactly the behavior that we see here. Okay, now in other regions, what you have is a behavior that we call a reset, okay, of the normalized Hall density. Your Hall density increases, and then it exhibits a drop close to 0 without changing sign, and then it increases again. Okay, this can be in red or in blue color. Okay, for positive or negative normalized Hall density. So let me show you a region where this happens. This happens here, for example, you go from light blue to dark blue, then white, and then light blue, darker blue. Okay, these resets, which occur in different regions, are associated with that cascade of phase transitions that I mentioned earlier for magic angle bilayer graphene. Okay, where you're spontaneously flavor polarizing, and then you start feeling other flavors. Okay, and then the last feature that I want to draw your attention to are features associated with Van Hove singularities. Okay, so in these cases, your normalized Hall density flips sign but diverging at the sign change. Okay, so you can, for example, go from light blue to dark blue, abruptly switch to dark red, and then light red. Okay, this is something, because at the von Hoff singularity, your Rxy goes smoothly through zero. Your Hall density, which goes as 1 over Rxy, diverges and flips sign. Okay, this is something that you can see, for example, here. You go from light blue to dark blue, abruptly changes to dark red, and then lighter red. Okay, and it happens also here, and it happens in various places. Okay, so now we have these two phase diagrams, okay, for the resistivity and for the Hall density, and we can try to see if these, anything is correlated between these two phase diagrams. Okay, now because superimposing them would be too complex, I'm just going to superimpose schematically these two phase diagrams. So what I'm going to do is I plotted here the superconducting regions, okay, as a function of filling factor and displacement field. Okay, dark blue means robust, strong superconductivity. Light blue means weak superconductivity, still present but is weaker. Okay, and then I'm going to now superimpose in this diagram the regions in the normalized Hall density where we saw gap Dirac behaviors here in red, reset type of behaviors in orange, and von Hoff singularities in these dark blue lines. And now something is emerging. Okay, you can see that at low displacement field, the superconductivity is mostly bounded between the resets that occur at 2 and 3 and -2 and -3. But at high displacement field, your superconductivity is bounded by von Hoff singularities and gap Dirac points. Okay, so let's focus. Let's look a little bit more in detail to this. Okay, so let's look at this diagram and let's look at the properties along this dashed line, which intersects a von Hoff singularity here, as you can see. Okay, so if we measure the resistivity, it's of course 0 in the superconducting state, and then it becomes finite when you come out of the superconducting state. Okay, now we can measure the critical temperature, the BKT transition, as a function of filling factor along the same trace, and it's finite, and of course it's 0 the moment the system stops being superconducting. Okay, now along this trace we can measure also the effective mass of the electrons, okay, by measuring the magnetic, the temperature dependence of the Shunikov that has oscillations. That effective mass is proportional to the density of states in the system. That's plotted here, the effective mass as a function of filling factor along that trace. You can see that as we approach this region, the effective mass diverges. Okay, in fact, this point coincides with that von Hoff singularity that we have here, where your density of states is expected to diverge. Okay, and what you can see very interestingly is that superconductivity ends at the von Hoff singularity. Okay, this is very much unlike typical weak coupling BCS type superconductivity. Okay, in a typical conventional superconductor, as your density of states increases, your TC grows exponentially. Here, as our density of states increases, TC not only it doesn't grow, it actually decreases, and it becomes 0 at the point where you have the maximum in the density of states. Okay, so this is very unlike weak coupling BCS type superconductivity. So let me show you that the system actually realizes ultra strong coupling superconductivity. So you can measure this BKT transition versus filling factor and displacement field. Okay, I show it here in this 3D plot. Let me project it onto top plane here. As you can see, the superconductivity is, has the highest critical temperature in this region, and this region, as I showed earlier. Because this is a bit complex, these color plots, let me show you a cut as a function of filling factor of TBKT as a function of filling factor at optimal displacement field, and then at optimal density, at optimal filling factor as a function of displacement field. Okay, so this is TBKT at optimal electric field as a function of displacement field. As you can see, there is a very small dome for electrons and a much bigger dome for holes. This is around 2 holes per Moiré unit cell. Okay. Now, in this same plot, I can show you what is the superconducting coherence length, Ginzburg-Landau coherence length that we measured as a function of density. And it's like this. Okay. It decreases as you reach, optimal doping, and then it increases. Okay. Now, this is an extremely short superconducting coherence length, because you have to remember that the system, these Moiré superconductors are the lowest charge density superconductors that exist by far, by more than an order of magnitude. Okay. In fact, let me plot here what is the average interparticle distance as a function of filling factor in the system, and it's like this. Okay. So you can see that near optimal doping, your superconducting coherence length is actually of the same order as the average interparticle distance. Okay. We can do this also, look at TBKT as a function of displacement field. Okay. We can measure also the superconducting coherence length. This is all at optimal doping, and this is the average interparticle distance at optimal doping. Okay. Now, in a weak coupling superconductor, your superconducting coherence length, tells you what's your Cooper pair size. Okay. As you can see, at optimal doping, your Cooper pair size is less than or equal to the average interparticle distance. Okay. In the strong coupling regime, it's not so clear that you can interpret it in this way, but if anything, it's an upper bound. Okay. So now this this thing is reminiscent of the situation that occurs in cold atoms, where you have a BCS to BEC crossover. Okay, so this picture is from the review from Mohit and Herrero, where in the cold atoms community you have this tunable knob, this flashback resonance that allows you to go all the way from the tune the interaction strength such that you go all the way from the BCS limit, where your Cooper pairs are very large compared to the average interparticle distance, all the way to the extreme BEC limit, where you have tightly bound pairs of fermions, which are very diluted. Okay, their distance is much closer than the average interparticle distance, and the BCS to BEC crossover occurs roughly when the Cooper pair size is of order the interparticle distance. Okay, now this in 3D there is a critical temperature over TF upper bound of 0.22 in 2 dimensions. It is a TBKT over TF upper bound, which is 0.125, which is reached at the BCS to BEC crossover. Okay, now because we can measure the effective mass and the density of our carriers, we can measure the Fermi temperature, and we can also, let me show you here the effective mass as a function of filling factor. We can also measure TBKT as I showed earlier, so we can plot TBKT over TF as a function of filling factor. You have this behavior. This is at optimal electric field. We can do the exact same thing as a function of displacement field at optimal density. Okay, and you have the TBKT over TF. As you can see, okay, this is the dashed line indicates 0.125. As you can see, TBKT over TF reaches values in excess of 0.1 with the maximum at 0.125 for this system. Okay, now I don't want to make too much a deal out of this exact 0.125, because those calculations that I showed earlier, that upper bound is for a system of cold atoms, where the mass of the boson is clearly twice the mass of the fermionic atoms that both condense. For the case of electrons, this doesn't need to be necessarily the case, but still, this system reaches values of TBKT over TF, which are the highest for any superconductor. Okay. In fact, usually we characterize how strongly coupled superconductors are by looking at a log-log plot of TC over TF. Okay. Conventional superconductors, they tend to be around this region. For example, aluminum, which has a 1 Kelvin TC, okay, and a Fermi temperature, which is same as density normalized by various factors here, so that you can compare 2D and 3D superconductors. Aluminum has a Fermi temperature of over 100,000 Kelvin. So given the gigantic density of electrons that aluminum has, it superconducts quite modestly. Okay. Now this is the line for the BEC-BCS crossover in 3 dimensions. As you go in, towards this region, you go towards more and more exotic types of superconductors. And in particular, in this purple band, you have, pretty much all of the unconventional superconductors. You have cuprates, the pnictides, the organics, the heavy fermions, okay? This is the BKT, the upper bound, for the BCS-BEC crossover for TBKT, okay, in 2 dimensions. Magic angle twisted bilayer graphene, okay? If you, depending on whether you look at TBKT or 50% normal state resistance, those data points are here. For the trilayer case, those data points are here, okay? Magic angle twisted trilayer graphene is even more strongly coupled than the bilayer case, and it's in fact the strongest coupled superconductor that exists in the world, okay? Only recently, Iwasa's group has posted in the archive that lithium doped zirconium nitrogen chloride is another system where you can reach this line, okay, of ultra strong coupling superconductivity. Now, let me tell you in the last 10 minutes or so about an unexpected surprise that we found out when we started to do in-plane magnetic field measurements. Now, as I showed earlier, in a perpendicular magnetic field, if you are at optimal doping, superconductivity disappears well below 1 Tesla. This is due to the formation of vortices, the standard orbital effect in superconductors. Now, because magic angle twisted trilayer graphene is a 2-dimensional superconductor, we can apply an in-plane magnetic field and look at what is the effect of a purely Zeeman field, okay? Because you don't have vortex, formation due to an in-plane magnetic field. It would take hundreds of Tesla to do that, okay? So now, what is the usual Zeeman effect on conventional superconductors? Okay, well, conventional superconductors have spin-singlet Cooper pairs, okay, shown here. The binding energy of these Cooper pairs is given by the gap, which is 1.76 times kBTC. That's within the BCS theory of superconductivity. And Zeeman field breaks apart or splits, those spins, okay, such that when the Zeeman energy, Zeeman splitting, okay, which is GMBB, is equal to the superconducting gap, then superconductivity should be suppressed. If you put in numbers, okay, you have that there is this thing called the Pauli limit, the paramagnetic limit, or the Chandrasekhar-Clarkson limit, which tells you that this Pauli limit superconductivity should be well gone by the time you reach a field, magnetic field of 1.86 Tesla per Kelvin times TC. So for a TC of 1 Kelvin, superconductivity should be well gone by 1.86 Tesla, okay? That's for BCS spin-singlet superconductors. Now, let me show you what happens with our system. So we take our sample that we were measuring before in a perpendicular magnetic field, we warm up the system, we rotate it, we put it exactly in plane, okay? We measure again at 0 field, the system has, looks very, very similar. It has just changed a tiny bit with respect to before. We measure again critical temperature, 2.7 Kelvin at optimal doping and optimal electric field. That means your Pauli limit should be about 5 Tesla, okay? Superconductivity should be well gone at 5 Tesla. We measure with an in-plane field of 10 Tesla, and we see that superconductivity is very much still present at optimal doping in an extended region of displacement field, okay? Now, we can first check that indeed this is superconductivity. It is, if you measure the critical current, as a function of magnetic field, you can see that it continuously decreases, but, I'm zooming in here for 8, 9, 10 Tesla. It's very much still finite, your critical current at 10 Tesla in play, okay? We can do this more, study the strongest superconducting dome, the one between -2 and -3 holes per unit cell, okay? As a function, continuously as a function of displacement field and filling factor at different parallel magnetic fields, we see that it shrinks the superconducting region continuously, but it remains finite. So superconductivity, exists in fields, in excess of 10 Tesla. Now, in order to study by how much we violate the Pauli limit, we have to do temperature dependence measurements, okay? So we can look now, again, this system is extremely tunable. So I'm showing different cuts in a 5-dimensional plot, okay? So we have resistivity versus filling factor and temperature. This is the usual superconducting dome, doping and temperature. And we can do this at different parallel magnetic fields. You can see again that at 10 Tesla, we still have a finite superconducting dome, okay? Now I can take a particular density, filling factor, and measure continuously your resistivity. The resistivity is a function of temperature and parallel magnetic field, okay? You can see this here. This dark region is superconductivity. I can take any threshold that I want for superconductivity, 10% normal state resistance, 20%, 30%. It is the same if you take 50% or BKT temperature, okay? You can see that these regions are evolved all parallel, okay? The contours follow this quadratic form, okay? So these are all parabolas, okay? And if you calculate what's the Pauli limit for each of these thresholds, they have corresponding Pauli limits, okay? Which are here. As you can see, superconductivity survives up to much, much higher fields than the Pauli limit. In fact, at this filling factor, the Pauli violation ratio is over a factor of 3, okay? Now, what are possible mechanisms that lead to Pauli limit violation, okay? Because there are actually, a number of superconductors where this Pauli limit is violated, okay? The most typical mechanism is very strong spin-orbit coupling, okay? That happens, for example, in the transition metal dichalcogenide superconductors. If you take monolayer niobium diselenide and you apply an in-plane field, you can see that the Pauli limit, which is this dashed line, gets violated by a lot. That's because you have very strong spin-orbit coupling in niobium selenide. You have this ISIM type superconductivity where your Cooper pairs are locked by 1,000 Tesla, spin-orbit induced magnetic field, which means you have to apply a lot of in-plane magnetic field to do anything, okay? However, graphene has an extremely small spin-orbit coupling, okay? Orders of magnitude smaller than these systems. So it is very unlikely that spin-orbit coupling will be able to explain our huge Pauli limit violation, okay? It would have to be, about a factor of 30 larger than it is in graphene, in Magic Angle Trilayer graphene, in order to begin to account for the Pauli limit violation ratios that we observe. Another possibility is finite momentum pairing, FFLO states, okay? In those cases, those superconductors, which are only a few that realize this, okay? You can have an enhancement of your Pauli, of your critical field above the Pauli limit of order 20–40% at low temperatures, below half of TC, okay? This again is very unlikely in our case, because first of all, we see an enhancement of 300%, not 20%, okay? And in addition, our Pauli limit is violated right away from TC, starting from TC, okay? Not only at very low temperatures, but right away, we violate the Pauli limit, okay? Then one last mechanism is the possibility that due to, the strong coupling superconductivity, you have preformed pairs with a pseudo gap, where in that case, the critical temperature has nothing to do with your pairing amplitude, but it has to do with your superconducting, with your superfluid density, phase stiffness in your system. However, in our system, we can measure, the superconducting coupling strength as a function of filling factor, and we can see that it varies by over an order of magnitude. Okay, we have very strong coupling, near this region, but relatively weak coupling, near the edge of the domes. But if we measure the Pauli violation ratio as a function of filling factor, we see that it does not depend, very strongly, and it's always above 2, in the entire superconducting dome. Okay, even in regions where the coupling strength is much, much weaker, and we don't expect to have, big preformed pairs, big energy preformed pairs. So, moreover, none of the mechanisms that I have just told you about can explain this reentrant superconductivity, which we observed, at higher magnetic fields. Okay, so the data that I have shown you are at optimal, this Pauli violation data, where as a function of density of filling factor at optimal displacement field. Okay, if we measure at less than optimal displacement field, then we have the following. Okay, I'm focusing now only in the high magnetic field region. We see that our resistivity decreases, our critical temperature, decreases continuously until it goes to 0. And then another superconducting dome emerges, at high magnetic field, okay? We call that superconducting 1 and superconducting 2 regions, okay? We see this not only in the critical temperature, but we all in the BKT temperature, we see it also in the critical current, okay? The critical current as a function of parallel magnetic field, okay? Again, I'm focusing only here from 5 Tesla upwards. The critical current comes from very high down there, and it decreases, becomes pretty much 0, and then starts to grow again, okay? Now, there are very, very few systems where you have low field superconductivity and a reentrant superconducting phase at high field, okay? In particular, the systems, that show both of these behaviors are, the uranium family compounds, okay? And it's most prominent is this uranium, germanium 2 to uranium, rhodium, germanium, cobalt, germanium, and then ending with uranium Te2, okay? In these systems, you can have high field, reentrant superconducting phases, and this superconductivity violates the Pauli limit. Perhaps the most spectacular system is this recently discovered uranium Te2. All of these systems are nearly ferromagnetic, or either ferromagnetic, or in the case of uranium Te2, nearly ferromagnetic. Okay, and it is believed that these systems realize triplet superconductivity, in particular in the case of uranium Te2. Okay. Now, in our system, because again we have many tuning knobs, we can see that indeed there is a field-induced, phase, superconducting phase at high field. We can look at this as a function of displacement field near optimal doping, or as a function of filling factor, at a given displacement field, shown here, okay? You can see that we have superconducting 1 and superconducting 2 regions. These regions are extended over, a range of parameter spaces. In some cases, we even sometimes see a few extra regions which, resistivity doesn't reach 0 there, so we're not sure if those are fragile superconducting phases or not. But these ones are very robust. Okay. Now, let me just say that the results, from this, this magnetic field high Pauli violation limit and reentrant superconductivity tells us that this system, Magic Angle Trilayer graphene, is very likely spin triplet superconductor, or certainly at least a non-spin-singlet superconductor. Now, in the last minute, let me tell you, so I don't want to go through this summary. I think I already mentioned it. You just heard about all of this. Let me tell you that we have a recipe in principle now to make alternating twists with multi-layer systems, so that, I hope, in a few months, or, either my friendly competitors or myself will be telling you about Moiré Magic 4.0 and 5.0, etc. It's not clear what symmetries are responsible for this robust superconductivity, but the group of Ashwin Vishwanath claims that C2ZT is essential. T is time reversal symmetry, and C2Z is a 180-degree rotation in plane. Magic Angle Bilayer and Trilayer have that symmetry. All of the other Moiré systems, which do not exhibit superconductivity, do not have that symmetry. Okay, so, and then, there are tables of what is spatial symmetry of, for different, order parameters, and all the parameters for different spatial symmetries can be, and you can find them in these type of papers. I hope to have shown you that we can realize, almost all of the phases of condensed matter, using very simple ingredients, graphene. In the case of, recently we've realized also Moiré ferroelectricity with, hexagonal boron nitride. You can also do many of these phases, magnetic and topological nematicity with TMDs. Imagine, but this is just the beginning, just with these very simple ingredients. Imagine what we can do, the infinite possibilities that we have, if we start using more complex two-dimensional materials, such as high TC cuprates or tantalum disulfide, ferroelectrics or quantum spin liquids, and we start twisting them and creating Moiré patterns with them, okay? In fact, theories are already calculating all of this. For example, here is work from Canada, the group of Mansell, France, has predicted that if you take 2 monolayer cuprates and you twist them by a large angle, you will realize high temperature topological superconductivity. It's not small twist angle. Actually, now it has to be a large angle, above 30-something degrees. The group of Leon Valens has been working with, twisting two-dimensional crystalline magnets. You can form these Moiré magnets with special Moiré fermions and all kinds of spin textures. Basically the field is wide open. Moreover, you can go beyond condensed matter physics. People are already looking in cold atoms at Moiré and twisted, cold atom lattices. People are looking at classical mechanical systems in Moiré and twisted phononics. Okay, you can also realize Moiré and twisted photonics. Okay, where you can slow light to a halt, by making flat bands for light. So all of this is growing, into many different directions. So with this, I want to end and acknowledge my group members. What I showed you today was largely the group of Yuan Sao and Jay Park, together with Daniel Rodan for some experiments. Plenty of collaborators. I hope we soon are able to get back to this type of events. And I want to thank the sponsors. And I want to thank you all for your attention. I want to note that I'm a CFAR Quantum Materials fellow, so I enjoy very much the Canadian hospitality and friendship and very interesting discussions with the Canadian community. And thank you all.
Great. Thank you so much, Pablo. All right. So yeah, time for questions. Let's see that anyone has hands up. Okay. So Graham, do you want to unmute yourself and ask a question?
Hi, thanks. A very interesting talk. Incredible data, things like that. One of in the spin triplet, one of the ways you can test for a spin triplet superconductor is looking at the spin susceptibility, for example, in an NMR measurement or a night shift measurement. Obviously, you don't have so many atoms in your sample, but have you thought about some way to probe the spin susceptibility?
So indeed, we would love to be able to do, a night shift measurement in the system, but as you said, we have, a few thousand atoms in the system, okay? Maybe a few 100,000 atoms. We do not know if the technique has that sensitivity, probably not. Now, we can, there are other ways to measure spin susceptibility, and in particular magnetization of the normal state, so to see, what happens in the normal state, and to see if the system is spin polarized or something like that. We are planning experiments to carry out those measurements. We have done such measurements with Magic Angle Bilayer Graphene. We haven't done them yet with the Trilayer, but we hope that those measurements will tell us, will give us some information. There are also, you can do also tunneling measurements, for example, spin polarized tunneling measurements to see, at high field if the system likes actually to superconduct the opposite. There are a variety of things. The systems are highly tunable, but they're very small. So we can do things like neutron spectroscopy. It's hard to do NMR. Other types of measurements. It's hard to do them. But I believe, some of the experimental techniques with improvements in resolution, we will be able to apply them to these two-dimensional superconductors too.
Great, thank you.
Okay, any other question? Yeah, maybe I can ask. There is one from Stefan.
Yeah, thanks for a nice talk. I wanted to ask, you showed in high magnetic field this superconducting feature goes to rather narrow filling fractions. Is this close to 2.5 filling, or is this any special value that one could understand?
So it survives. The superconductivity survives up to the strongest field in the region where TC is the highest. Okay, so that's near optimal doping. Okay.
So that's the strongest coupling region by the ratio.
That's the strongest coupling region. It's also the highest TC. Okay.
Okay, thanks.
Okay, maybe I can just ask another one. Okay, after that I can probably, we have another one here, but what about this C2Z symmetry that you mentioned about? Is that somehow related to spin triplet that are forming between the pairs related by C2Z? Is that why that's essential?
So C2C means 180-degree rotation with respect to a perpendicular axis to the plane of the superconductor. Okay. Now, in this work, actually not in this paper, in a subsequent paper that I haven't listed here, the group of Ashwin Viswanath said that they proposed a new mechanism for superconductivity. It's entirely due to Coulomb interactions, and they call it skyrmionic superconductivity. Okay, where the Cooper pairs are actually pairs of skyrmions. Okay, they form a BEC of skyrmions actually, and they claim that for that mechanism to work, they need to have exact degeneracy between two sets of Chern bands. Okay, and in order to have that degeneracy in that Chern sector, they need to have that C2C symmetry and also T. So they need to have C2C T symmetry. Otherwise, those Chern bands are not degenerate. Now, it is interesting that they said in that paper, magic angle twisted bilayer graphene has C2C T symmetry. Let me tell you which systems have it. And they said mirror-symmetric magic angle twisted trilayer, and then they also said a 4-layer, 5-layer with specific alternate twists. So they said, go measure the trilayer and see if it is superconductor. Okay. Now, at the time that they wrote that paper, there were a whole bunch of other Moiré systems where it seemed initially that there may be superconductivity there, because people saw resistances that dropped close to zero, some nonlinear VI curves, but they weren't like sharp switching. So initially people thought, oh, maybe there are other superconductors. Those did not have C2CT symmetry. So in the paper, Ashwin and collaborators were not like pushing so strongly because there seemed to be some evidence that there were other superconductors. But then later studies have found out that those other systems are very likely not superconductors. Or if they are superconductors at all, the superconductivity is extremely fragile. Okay, they haven't shown Josephson phase coherence. They haven't shown all the things that you want to see for a robust superconductor. So now, with the discovery of magic angle twisted trilayer graphene, the Viswanath group has come back and said, you see, all those other systems don't have C2CT symmetry. They are not robust superconductors. The only two so far discovered which are robust superconductors have C2CT symmetry. We think maybe our mechanism, is due to the mechanism that we're proposing. We have to do more experiments, measure other layers, etc., to check that indeed this is the case. Okay.
Okay. But that's essential for a superconductor or essential for a triplet superconductor?
No, it's essential for the superconductor that they have proposed, this skyrmionic superconductor.
Yeah. Okay.
They don't tell you, whether in their paper where the system is spin-singlet, triplet, or combinations of singlet and triplet, one which is called, for example, spin-valley locked, okay? Because all of those states are relatively close in energy, and now, the same mechanism can give you all of those pairings, actually, okay?
Okay, we have another question from Adam Chen. Do you want to unmute yourself and ask a question, or do you want me to just read your chat question? Adam?
He's saying, please read.
Oh, okay, all right. So he says that, is it understood why only doping away from certain CI, the correlated insulator state, yield the superconductivity?
So it is not entirely understood, but what our experiments in the trilayer graphene case have shown us is something very interesting, which is superconductivity emerges from the state of your system where you're occupying two flavor-polarized states. In other words, you have two Fermi surfaces in your system, as opposed to 4, 3, or 1, okay? So this is something, I think I have a hidden slide here. Oh, sorry, this went out. I'll put it back in a moment. Let me show the hidden slide where I can show this, yeah. So where does the superconductivity emerge from in the system? Okay, so you can see that at low displacement field, it's in between these two resets at 2 and at 3, okay? And at high displacement field, it's bounded by von Hoff singularities and this gap Dirac, okay? So the superconductivity arises upon doping the nu equals 2 broken flavor symmetric ground state. What does it mean? Okay, remember that I told you that we had this cascade of phase transitions. At each integer, the system flavor polarizes. Well, at at small displacement field, you can see if you measure the Shudnikov-de-Haas oscillations as a function of perpendicular magnetic field, you can see these things pointing always outwards, away from charge neutrality. Okay, charge neutrality is in the middle. If you have holes, you point to the left. If you have electrons, you point to the right. Okay, that is telling you that at each integer, we have a reset at a new Fermi surface opens, okay, which has a spontaneously flavor polarized system. Okay, now the degeneracy of your Landau levels tells you how many Fermi surfaces you have. So it's 2 in particular after nu equals 2. Okay, it's 1 after nu equals 3. That again tells you how many empty flavors you have. Okay, now if you go to large displacement field, what we noticed is that we start to see Landau fan diagrams also pointing inwards towards charge neutrality. Okay, that tells you the following. In particular, the most interesting is what happens around nu equals 2. Okay, so around nu equals 2, we have a fan diagram pointing inward, and what that is telling you is that in this region we have superconductivity, but the superconductivity that occurs is because we have a reset that has occurred where your Fermi level has been sent not to charge neutrality, but it's a strong reset to send your Fermi level under the charge neutrality point to the whole doping region. Because you have holes, now they point towards the left. Okay, so what we believe that is happening is that this Van Hoff singularity here is triggering the phase transition, the cascade of phase transitions, that typically occur at the integers due to Coulomb interaction. If you have a nearby strong Van Hoff singularity, it can trigger that phase transition at an earlier filling factor. And because it occurs before nu equals 2, your reset sends you to the whole region. You have 2 Fermi surfaces, but whole dope. And then you go through 0 and then to electron doping. But you can see superconductivity, and that tells you that superconductivity happens when you dope with electrons or with holes that 2 Fermi surface state, okay? That 2 flavor, 2 empty flavors state, okay? And that's what we believe, is happening. So at small displacement fields, you have these resets, and superconductivity occurs between 2 and 3 or between -2 and -3. At large displacement field, a Van Hoff singularity kicks you in the reset to the whole doping region, and superconductivity occurs when you dope with electrons or with holes this spontaneously flavor polarized state with 2 Fermi surfaces.
Okay, yeah. So we had a couple of more questions. I recall that David had raised the hands earlier. David, do you want to go first? And after that, we have Andre-Marie.
Yes, sorry, maybe it's a repeated question, but I was just wondering about the ways to detect if any possible breaking of time reversal invariance occurs.
Mm-hmm. So indeed, that would be very interesting to see if it happens. Okay. Now, this theory mechanism that I mentioned earlier, is based on C to CT invariance, but we don't know if that's a mechanism. I think that one of the most interesting things that we could do to start with would be Kerr measurements, okay? Kerr rotation measurements, like such as those that the group of Aaron Kapitulnik have done in other superconductors which break time reversal invariance. So I think that that would be one of the first things that I would try. It should be in principle sensitive to that if it is there.
Yeah, yes, thank you.
Andre-Marie?
Yes, thank you for this nice talk. So at the beginning, you mentioned that there was a canonical transformation in the Trilayer case that, if I'm not mistaken, led to bilayer plus single graphene, right?
Yep.
So if I go back to the real system, there is no broken top-down symmetry, despite the presence of interactions. Is that right?
There is mirror symmetry with respect to the middle layer in A twisted A stacking Trilayer graphene. Yes.
Okay, that survives. I mean, the thing is just a canonical transformation. It's not.
Yes. It's just a phase it's just a
canonical
basis transformation. Yes. Yes.
Okay. Thank you very much.
Okay, Stefan.
Yeah, thanks. I intended to answer this question, I guess, but I can ask a different question. And sorry for asking all these theory questions to you.
Oh, please, please.
But is there actually, you have this C2Z times time reversal symmetry. Is there actually a way to break only the product and not break, let's say, the C2Z or the time reversal individually?
So I don't know. Okay.
Because it seems somehow, I mean, I can't really.
I mean, in principle, interactions can spontaneously break C2CT symmetry. That's something that has been seen in Magic Angle Graphene graphene, so that you can go into a quantum anomalous Hall state, okay, at zero external magnetic field due to interactions. Now, in terms of trying to engineer it, I know how to break C2C. For example, by aligning to hexagonal nitride substrate, you can break C2C rotation symmetry. I don't know a way of engineering, on purpose and tuning.
Yeah, presumably it would have to be some weird kind of magnetic structure which only breaks the product.
Perhaps, yeah. Perhaps if you, maybe if you put a 2D magnet, with spin, with magnetization in one direction top layer and another one in the bottom layer opposite, or something like that, you could break, or the same actually, then you would break C2CT. I don't know, maybe something like that.
Yeah. Okay, thanks.
All right, I think that we had lots of questions for Pablo, so it's time to let him go. So let's thanks again for wonderful talk, and
thank you.
I hope you enjoyed.
Thank you.
Thank you very much, everyone.
Thank you so much, and I'll see you again in a month.